Hi, everyone. If you're here for Science and Nature Untapped, you're at the right place. I'm just going to begin with a little bit of housekeeping. So we love to know where you're tuning in from. And then if ever you have any questions, you can put them in the chat section on the Facebook Live, and we'll get to those questions at the end of the presentation. So welcome back to Science and Nature. This is a free virtual monthly speaker series brought to you by the River Institute. My name is Stephanie Hildebrand, and I'll be your host for this evening. Before we begin, we'd like to acknowledge that we're on the traditional territory of the Haudenosaunee. We offer our gratitude to the Mohawks of Akwesasne for their care for and teachings about our earth and our relations. In honoring those teachings, we are committed to the process of dismantling the ongoing legacies of settler colonialism through good relations with each other and the lands we live and work on. The River Institute was founded in 1994 in partnership with the Mohawk Council of Akwesasne. We are committed to listening to and working with our partners through all that we do, and we're grateful for the time and knowledge that our neighbors graciously give to us, and we strive to improve the health of the Great River and surrounding lands. This relationship extends into our personal lives as we get to know each other and build relationships outside our time at work and through mutual interest in the health of the environment. And so with that, you might not be tuning in from Cornwall, Ontario, or the St. Lawrence River. You may be tuning in from California, as our speakers are, or from anywhere else around the globe. I highly suggest you check out the website native-land.ca. If you would, well, I think everyone should know whose territory they're living on, working on, or visiting if you're on vacation. If you're in Canada, you can text the 1907-312-5085, the city and province that you're in, and you'll get a text back of whose territory you're texting from. If you're interested in learning more about what the River Institute does, upcoming events, educational programs, research, you can follow us on social media. We are on Twitter, Instagram, and Facebook. Otherwise, if ever you wanted to listen to a Science and Nature Untapped event or a presentation that we've had in the past, you can go to riverinstitute.ca/untapped. And all the videos will be there and linked to our YouTube channel. So you can watch them over and over again if you'd like. For upcoming events, we're gonna have Dr. Ajitsa Horn on February 4th, 7 p.m. This will be a hybrid event in person and on Facebook Live. We're still finding a location for this talk as our regular location will not be available. And so her talk will be Ganyat the Wolona, the Great River, her health, and the health of the future. If a lot of events like Science and Nature are supported by donors, if ever you wanted to make a donation to the River Institute for research, education, or events such as these, you can do so at riverinstitute.ca/donate. Otherwise, just sharing our social media, talking about us to your friends goes a really, really long way in supporting us. So for tonight, we'll be hearing about fish inclusion for hydropower. We have two speakers coming out of San Francisco. First, we have Abe Schneider. He's a co-founder and chief technology officer of Natel. Abe creates hydraulic designs for Natel's turbines and works at the intersection of science, R&D, products and project development, and communications. Abe holds bachelor's and master's degrees in mechanical engineering from MIT. Abe enjoys surfing, wing foiling, rock climbing, and building things with his wife and two children. And then we have Sterling Watson, who's a staff engineer and leads fish safe turbine design at Natel Energy. Her technical focus includes turbine performance assessment, fish passage test design and data collection, engagement with the scientific and stakeholder communities, and model development to inform high performance, fish safe turbines, and hydropower plant designs. Sterling holds a bachelor and master's degree in mechanical engineering from MIT. Her passion for everything aquatic extends beyond the office, and she can be found swimming, surfing, sea foraging in the waters of San Francisco during her free time. So thank you so much, Abe and Sterling, for joining us this evening. You can share your screen.
Thank you, Stephanie.
Thank you, Stephanie.
Can you see the screen?
Yeah, I think you're good.
Great.
All right, well, thank you very much for the opportunity to participate in the Science and Nature series. We are excited to share the work that we're doing to allow for safe downstream passage of fish through hydropower turbines, and in doing so to help solve some of the issues related to sustainability of hydropower and river connectivity, which is a big issue as we're trying to make progress towards a zero carbon future. Our company, Natel, is a small company based in California. We have two primary areas of focus, both related to water and to energy. We have a group which focuses on the design of turbines safe for fish passage. And we have a group called Upstream Tech, which is a world leader in water forecasting using modern artificial intelligence methods, as well as automated landscape monitoring. You can learn more about both of our companies at natelenergy.com and upstream.tech. Our work is inspired by nature's engineer, the beaver. Beavers are a personal inspiration to me in showing how to build infrastructure that can provide ecosystem uplift. And as the photograph from the right shows, beavers were a big part of my childhood. A lot of the work that we do at Natel is based upon ideas that my dad, Daniel Schneider, in the center on the left, was deeply interested in, specifically sustainability and sustainable energy systems and fluid dynamics. And under the table, actually that's not a table, that's an airfoil that he's holding. And if you look under the airfoil, you can see a little child, and that's my co-founder and sister, Gia. She's also the person in the right-hand picture. And what we're doing in this picture is using a Hess sampler to collect and then count aquatic macroinvertebrates to quantify the health of this particular stream. And this stream was one of twin forks. One of the forks ran through an area of the watershed that was managed for multiple uses, including cattle grazing. And some of the ranchers would take out the beaver dams in that fork, thinking that the beaver dams flooded the meadows, but actually the beaver dams were essential in the creation of those meadows. And the other fork passed through wilderness territory, and the beavers were undisturbed. I just knew that the fishing was better in that fork, but as a high school student, I wanted to understand more quantitatively the differences, and so that led us to this particular project. Turns out that there was a significant difference, an increase in the number of beneficial macroinvertebrates in the stream that had healthy beaver activity. So this motivates our work today, and it's really interesting to come back in 2022. Beavers made a big splash in the media because of their role preserving critical parts of ecosystems in the American West, as severe drought led to pretty devastating wildfires. And this is an image taken from Vox showing a stream basin with beaver activity, and it's the only remaining green area in this entire landscape. And it's because of the effects that their small and porous dams have on the surrounding riparian zone, increasing the quantity of water in the soil and keeping all those plants healthy and green. So beavers are one inspiration for showing us how we can do infrastructure better. And that's really important when we take a look at some of the issues with migratory species and hydropower. So I sincerely apologize to the audience, which if you're from Canada, we really need to extend this map to include Canada as well. But this is a map of the United States showing the water basins, the river basins, and in green are basins where eels have presence, American eel has presence, and then the purple dots represent hydropower facilities. And one of the shocking things to me is how truly widespread eel are in the United States. They basically can be found in almost every stream that touches the Atlantic Ocean. And in addition, they affect a very, very large fraction of the installed US hydropower fleet. So almost 1,000 hydro plants in the US lie on territory of the eel, representing over 30 gigawatts of generating capacity. This is a huge fraction of the United States fleet. And you can see that a large concentration of very small dots exists in the Northeast. And this is a problem because eels are an animal that travels upstream as babies and then grow big up in the headwaters. And then when they reach maturity, sexual maturity, they must travel downstream as big animals to go out to the Sargasso Sea to complete their life cycle. And that's an inherent issue because they need to pass through potentially numerous hydropower facilities on their way to the ocean. So looking at another map, again, of the US, but in this case, it shows both a problem and a real opportunity. So here are all the hydropower projects in the United States which require relicensing by FERC. So in the US, hydropower facilities operate on 50-year licenses, and at the end of that period of time, the license conditions are renegotiated. And what we're seeing is that there's an increasing priority by the public for biodiversity, for ecosystem health, in addition to clean energy. And a lot of intense focus is now being placed on the effect that hydropower facilities have on the ecosystem, including for fish passage. There are hundreds of hydropower facilities which are undergoing relicensing in the next decade. And 70% of those projects are projects that are on eel territory. And a lot of those projects are relatively small, leading to a pretty severe issue with eel passage. The other important aspect about the US fleet, and this is true of also the Canadian fleet and the European fleet hydropower plants, is the average age of all these facilities is quite old. In fact, it's over 50 years. And so a lot of these facilities are already needing to make investments in refurbishing and modernizing their turbines simply to keep them operating. And so what this shows is or what it presents is a real opportunity to make a wise decision to both modernize and relicense these plants with an eye towards improving safe fish passage.
So this is an image that was taken downstream of a dam in Maine. And this may be a familiar sight to some of you who work or live or play near rivers in the vicinity of hydropower dams. The two species that are pictured here that were found injured or killed downstream of a large dam are American eel and juvenile alewife. And these are actually both species that we've conducted our own studies to understand how to design specifically for. So just like Abe was saying, at this point in time, we actually have a major opportunity to improve the way that fish pass downstream through hydropower plants. And out in California, we have some different migratory species than what is over on the East Coast, but we are still very familiar with the St. Lawrence River and specifically how important a watershed that is for the American eel. We got the chance to come visit for the joint meeting of anguillid eel and sturgeon researchers back in October of last year, and see, exactly firsthand the situation of eel passage in the vicinity of the Moses Saunders Power Dam.
So in this photograph, we're actually looking at some carcasses of eels downstream of Moses Saunders.
So this is the current situation when hydropower turbines are not safe for fish. When the turbines are not safe, really the only options are to either screen the turbines and give fish alternative pathways around the plant, or to require turbine shutdowns, particularly during migration periods. And in some cases this can work, but it's a very difficult solution because it's a trade-off of what flows can be used for hydropower generation and what flows can be used for fish passage. And so when you have a situation like this, a situation of fish exclusion, then the fish need to find a very likely small fraction of the flow to be able to complete their downstream migration. And besides that, you have risks of fish still managing to pass through screens or get injured on screens and incur mortality through that infrastructure as well.
And this needs to be done on potentially numerous power plants in series, all the way from the headwater down to the ocean.
So an alternative solution to accommodate hydropower generation as well as safe downstream fish passage is to actually design the turbines so that they function as safe downstream passage routes for the fish. And so that's what's pictured in the diagram here. In this case, all or nearly all of the downstream flow is opened up as migration routes for fish. So this can improve fish's ability to find a migration path quickly and effectively. It also simplifies the design of the site and reduces the complexity of site-specific engineering and studies to understand how well the site will perform with fish passage. So just to take a step back, we've mentioned this term fish-safe hydropower, and this is something that we want to make sure is really well defined. So truly fish-safe from our perspective means having a negligible effect on fish populations in a watershed context. And so that may vary for different species and life stages and rivers. But just to give an example, if you have a river that has 10 hydropower plants in series and fish need to pass from the headwater all the way to the tailwater, then a 99.5% survival rate per site gives you a 95% survival rate for the population. And so true fish safety is can be a very high bar.
So Natel is certainly not the first group to think about fish safety and to put a lot of work into it. On this slide are a couple of examples of existing turbines which have found deployment, particularly in Europe. On the left is a VLH turbine, and on the right is an Archimedes screw. And both of these machines or turbines have been tested to show fairly high degrees of safety for passing fish. But they don't represent a vision for the rest of the hydropower fleet because of the fact that these types of turbines are very niche. They require very specific civil works. Their maximum power output is very small, and they're limited to application at very low head. So instead, what is needed is a way to rethink how turbines like these function in regards to fish safety. So on the left is a propeller turbine or a Kaplan turbine, and on the right is a Francis turbine. And these are the types of turbines that generate the majority of energy today from hydropower. And specifically, the turbine type on the left is a type of turbine that's found very, very commonly in Canada and in the US at projects that have, say, less than 100 feet of head. So in those types of turbines, the mechanism that kills fish is often mechanical in nature as opposed to pressure related. And it's because those turbines have blades that are thin, that move very fast, and in some cases have converging points where a fish can get stuck and pinched between a part that's moving and a part that's stationary. And so the question is it possible to improve strike survival by design? And the bottom line is yes. And we're building on work that was done about 10 years ago by Alden Research Lab. In this slide are a set of photographs that are taken from 1,000 frame per second high-speed videos of fish being struck by both thin blades and by thick blades. And what Alden discovered is that there's a very, very key ratio, which is the ratio of the length of the fish body to the thickness of the blade that it's being struck by. And that if that ratio is very small or close to 1, the fish can survive significantly higher strike speeds than if the blade is much thinner than the fish. And as Natel started to think about turbine design for fish safety, really look at these stills, these high-speed video stills, and it's really interesting to see some of the fluid mechanics that are going on. In the upper set of images, you can see that this fish is being struck by the approaching blade, but its body doesn't show any indication of that blade approaching until it's actually physically contacted. And then the fish sadly is sharply bent around the blade, and it's very likely to die from spinal fracture. But when that fish is struck by a thick blade, in this second image, you can see that the shape of the fish is actually conforming to the geometry of the incoming blade, even though there's no contact at all. And so what this is showing is that there's some work that's being done on the fish body by the fluid, which is being pushed by the blade towards the fish. And so there's no sudden change in curvature of the fish, and then it is able to slide off and live. And this results in a 50% increase in the safe strike speed of the blade. But this isn't itself sufficient to design a turbine that is as competitive as conventional turbines in terms of energy density. And we'll get into that in a second.
Yeah, so as our goal was to try to figure out how to design a turbine that could operate at higher speeds while still being safe for fish, we conducted a series of really fundamental strike studies at Alden Laboratory using their linear strike facility. So what you're looking at here, this big long blue tank, is it's a rectangular flume that has a set of rails that allows you to propel different representative turbine blade geometries across the flume, and different sizes of fish can be placed within the viewing chamber. So you can collect high-speed video of the strike event, as well as detailed injury and mortality observations afterwards. So we conducted a study here in 2019. The results were published in 2020. And we looked at how the size of the fish relative to the thickness of the blade, the L/T ratio, the strike velocity, and the geometry of the blade affected strike survival outcome. So that's been a very important data set as we've continued to develop our turbine designs. One thing that we learned from the analysis of the high-speed video from the strike study was a little bit of quantification around why these very thick blades improve strike survival outcomes. So as the L/T ratio gets smaller, or the blade gets larger relative to the size of the fish, that blade actually acts to push the fish out of the way. So you can see that at L/T ratios around 1, the fish can be slowed by close to 30%. And so the actual contact, if it occurs, is at a lower velocity. And that helps to explain why these types of blades can really improve the strike survival outcomes.
So I mentioned that this making blades blunt isn't enough to allow for a turbine to be as power dense or energy dense as a conventional non-fish safe turbine is. And in order to do that, we needed to allow for a significant further increase in rotating speed of the turbine, which could create problems because then the tip speeds get really fast. And so our approach to allow for a turbine to rotate with the maximum possible velocity while still respecting the biological limits of fish is to add a slant to the leading edge, which gives the turbine a very unique shape. So if you look at these images on the right-hand side, you can see that the leading edge of the blade is swept forward out towards the tip. The reason for that is that out at the tip, where the tangential velocities are highest, this slant allows for a reduction in the normal component of the strike velocity that the fish feel. And this allows for effectively achieving a uniform strike force all along the leading edge of the blade. And that's the hypothesis that we tested in the linear strike rigs at Alden Research Laboratory. So this gives you a sense of how a turbine designed with these principles might appear in comparison to a conventionally designed simple propeller blade. As you can see, the blade on the left has very thick blades that are noticeably swept forward. There's fewer blades, so there's less blades to contact than a conventionally designed propeller blade on the right.
So this is an example of how that type of fish-safe runner might be implemented within an entire turbine assembly. What you're looking at here is a pit-style axial flow turbine. And a few features to note are that there's actually no converging gap out at the tip section. So at the maximum radius of the blade, because we have that forward slant, not only does it help to reduce the force that the fish feels, but it actually sweeps the fish inwards towards the center of the blade, where it can then pass downstream rather than outwards into a converging pinch point where it can get severely injured or even severed. And this is an example of the size of eels that we have actually done testing with relative to our test scale turbine. We'll get into that in a few slides.
So at this time, we have implemented, there are 3 projects operating with RHT style turbines. One is in Maine. It's at an old mill that's been repowered with a fish safe turbine. Another is a project in Oregon. And excitingly, the most recent project is in Austria. It's our first European project. And that project uses a submersible turbine. So we'll take a closer look at a couple of these projects. This slide shows some of the some photographs of the Oregon project. This is the largest turbine that we've built to date, but not the largest turbine that we're in the process of designing. This is a 1.9 meter diameter runner. It's operating at a 5 meter head, producing 300 kilowatts. It uses a direct drive machine. It's very efficient, very simple in its operation. And this site has had 2 different fish passage tests, which we'll go into in more detail, achieved safe passage of a wide range of rainbow trout. And in this image, in the video, you can see one of those trout passing through the moving turbine with yellow balloon tags, which are used for its recovery. Natel is also in the process of building 4 additional units of this size at their full rated head. At 10 meters, these units produce 1.25 megawatts apiece. Here are a few photographs of our most recent installed project. This is a submersible fish safe turbine installed in Austria. And as you can see, the runner has only 2 blades, and this allows for a relatively small, fast-moving machine to still provide very, very safe conditions for passage of even surprisingly large fish through this plant. This plant is interesting because it doesn't have a powerhouse at all. The turbine just sits underwater and an electrical cable comes out for connection to the grid. So next we'll share more about our fish passage testing, both at small and large scale in lab and in field environments.
So this is just a quick snapshot of fish passing through some of the turbines that we've tested. We've tested several different species, but are in the process of getting publications out to describe that work. But I'll be talking more about the tests that we've done with American eel and also the tests that we've done with juvenile alewife. So this is what's in our backyard. This is a scale turbine testing facility, and originally it was constructed just to conduct conventional performance tests of the turbine. So characterizing its efficiency, power, flow, et cetera, across the entire operating range. But because the design for safe fish passage is so key to our work, we actually adapted this facility to allow us to insert fish into the pipeline, pass them through the turbine, and observe any sort of injury or behavioral changes across our operating range for this particular design. So just to walk through what's going on here, this is a constant recirculating loop. Fish are injected in this pressurized canister upstream of the turbine, where they then pass with the flow into the turbine itself, which is equipped with a transparent runner housing and high-speed video cameras. From there, the fish move downstream and are separated from the flow by an inclined wedge wire Iker screen to end up in this recovery tank where we can take a look at their condition. So our largest and most comprehensive fish study to date was with American eel. We conducted this study in fall of 2021. And the goal of the study was to go beyond just understanding, are these eels going to live or die under relatively extreme conditions of our turbine design. We really wanted to get a good look at how they pass through the turbines and how their condition and behavior change over time, both immediately after passage and after an extended hold period. Through consultation with various experts, we designed the study so that the size of the eels was actually quite large relative to the size of the small test unit. So you can see in the graphic here that a significant subset of the eels that we tested were actually longer than the diameter of the turbine that they were passing through. And just to cut to the punchline here, the question was, could relatively large eels pass safely through an RHT under known operating and physical conditions? And we did see 100% survival of both the treatment group and the control group. But I'll walk through how this study was conducted. This is just another slide showing what we mean by the relatively large size of these eels. So, so the size of the eels that we tested on the model scale, if those eels were to pass through a 1.9 meter diameter turbine, for example, the one that we have at the Oregon site, then they would actually correspond to eels that are larger than what you might even see in the wild, even in a place like the St. Lawrence. So for the study, we worked with a team of biologists from Pacific Northwest National Laboratory. Each eel was measured for length, weight, and girth, and tagged with a pit tag for individual identification over the course of the study. And then the eels were observed both for their swimming behavior with video, as well as placed in these transparent tubes to allow us to get photographs and note observations of their condition around the entire body. And this was done immediately before the eels were passed through the turbine, immediately after they were recaptured, and after a 48-hour extended hold period. So after their initial inspection, the eels were carried over to the injection station on the hydraulic test loop. What you see in this bottom left image is an eel that has been loaded into the canister and pressurized. And when the red ball valve is opened, that eel gets pulled down into the pipeline, passes through the turbine, and then pops out at the recovery tub. And that entire process takes approximately 8 seconds. At the same time, we had a team of high-speed video operators who were scrubbing through footage to capture the moment that the eel passed through the turbine. And with a good deal of practice, we were able to have a pretty good success rate of 80% of all eels that pass through the turbine being captured on video. So this is just an example of an individual eel from the study, the type of observations that we were able to make of its condition at the 3 observation stages, pre-test, post-test, and the 48-hour hold period. And that same eel is pictured here passing through the turbine. So the work that we were able to publish helps to explain, helps to draw some observations about how the passage event affects the condition of the fish. So that's available for you guys to check out. It was just published last year in Transactions of the American Fisheries Society.
Yeah, so on this point, I think this body of work is breaking new ground in revealing dynamics of eel passage through turbines, and this information is applicable not only to our types of turbines, but potentially to others as well. And I just want to highlight an example of this. I've heard personally theories about eels passing through turbines that they can somehow tell they're going to go through a turbine, and then they ball up into a, they turn themselves into a ball, and then they go through the turbine and then swim on downstream. And in the nearly 90% of the passages that we were able to directly observe through the turbine, the subgraphic F, which is the bottom right of the graphs on the slide, shows the proportion of fish that were swimming upstream or swimming downstream. And that's what the light blue and dark bluish green bars show. And then the gray is something else. And basically, none of the eels in the test passed through the turbine in a ball. So instead, they were either swimming upstream or swimming downstream, and then we're able to determine some trends in terms of the size of the eel and whether they were swimming upstream or downstream. So there's some theories about swimming strength that you could make, but we're learning a lot, and I think other researchers might be able to learn a lot from the data set as well. And so one of our goals with publishing this is to show some of the things that could be observed and hopefully inspire additional work to look more closely into some of the phenomena that we've shed some light on.
Yeah, so at the conclusion of the study, we actually had a large subset of the original group of eels remaining in our tanks. There was a fraction that we culled for X-ray observation, but these eels, because they were all already pit-tagged, we took the opportunity to look into another important question, which is how do these eels fare passing through the turbine again? This is relevant because many eels have to pass through multiple hydropower sites on their way to the ocean. And so we were able to repeat the exact same test 7 days after the original study. And again, we saw 100% survival of all the eels. So this is work that we are working on publishing.
This is one of the most exciting outcomes of our eel testing work to date, because it really underscores the possibility of really allowing eels to pass through potentially numerous hydropower facilities and keep on going.
So in the fall of 2021, we actually did another big study, and this one was at a field site looking at the passage of juvenile alewives or Gasbro through a small turbine unit, also 55 centimeters in diameter. And the reason we conducted the study at this location is because it happens to be located next to a very large natural alewife run. So we conducted the study right in the middle of that migration period. And we wanted to study alewives because they're a good representative Alocean species, and we know that they are exceptionally fragile and susceptible to injury and mortality just through their natural migration process. This study is in the process of being published. It was accepted for publication, and the results were really encouraging. We saw 100%, plus or minus 6.5% survival corrected for the controls. So this For this study, we were actually able to install a transparent half runner housing in the field, which was really valuable because we wanted to see if those same effects of the low L to T ratio and the slant angle would essentially move fish out of the way of the leading edge of the blade. We also, another special feature of this study was that we had a 100% recapture trap at the outlet. So because these fish are so delicate, we didn't want to use any sort of tagging or marking techniques. So we were able to capture 100% of the fish that passed through the turbine at the outlet. The test procedure involved capturing the fish at a nearby drop location and then holding them overnight and then passing them through the turbine in large groups. So groups of about 60 fish. There were two control groups. One of them was released into the pipeline just downstream of the turbine, as you can see in the bottom left image, and the other one was just held in tanks over the course of the study. And this is a small sample of the footage that we got of the alewives passing through the turbine. I really like this video because you can see the fish are passing through in different locations, different orientations, but actually in no case do we see a fish being struck in a severe way, conforming to the leading edge of the blade and moving with it. And so this is consistent with the results that we saw with extremely high survival rate. A little bonus result of this test was that because we had 100% recapture at the outlet, we actually captured other fish that were just naturally present in the mill pond. So this was really exciting for us. We captured a bunch of crayfish, many suckers over the course of the study, sunfish, one 40-centimeter long eel passed through, and all of these fish are actually passing through a 19-millimeter screen that is installed at the intake of the turbine. So these are fish that are passing through this site all the time. Also a 20-centimeter long black bass. And fortunately, we were able to see that all these fish are passing through unharmed.
Yeah, but this is really the vision, is to just allow the ecosystem to function. These fish chose to go downstream. They can do so safely. This is the vision for hydropower into the future. So we wanted to bring it back to a fish that you probably care a lot about, which are eel. And we wanted to show how the work that we've done compares to other tests of eel passage through existing turbines. And on this graph are plotted the graphical representations of the turbine type, as well as the tip speed of that turbine and the eel passage rate for a single passage. And the RHT test is illustrated in orange. It's the point at about 20 meter per second tip speed and 100% survival. And you can kind of just look at this, that there's a clear decline in survival as the tip speeds increase. And notably, the only other turbine that has been shown in testing to have 100% safe passage of eel is the VLH, down at about 7 meter per second tip speeds. And the closest turbine in tip speeds to the RHT test are units that where they achieved just over 90% passage success of eels, but with much larger turbines and similar or smaller eels to what we used in our testing. Natel is working now on hydraulic designs for turbines that increase the tip speed. Our goal is to see how far to the right we can push our design concepts to allow for more and more existing hydropower plants at some point in time in the future to be able to operate with fish-safe runners. And as a bonus, projects that might be in your backyard, Beauharnois and Moses Saunders, are illustrated here. Those plants have propeller turbines, fixed pitch propeller turbines, rotating with tip speeds near 30 meters per second. And those would be great candidates for designs of the type that we're developing. So in conclusion, where are we heading with all this work? The projects that have been built so far with turbines of the Restoration Hydro type have been small, but we're not thinking small. We're already working on turbine designs with runners past 4 meters and with power between 20 and 30 megawatts for an individual turbine. We're in the process of designing turbines for refurbishment and retrofit of existing power plants, like the unit shown on the right, where the turbines are being designed for existing facilities and allow for simply a replacement of the runner itself and keeping intact all the other aspects of the existing facility. So allowing for an upgrade in hydraulic performance and in fish safety with a minimum amount of cost and downtime. And doing all of this with good efficiency across a wide range of operating conditions, which is really essential for the project owners. So we think that this we're at a pivotal moment in time where we've been able to demonstrate the concept. We've been able to gather a lot of good data for different species, different life stages, different sizes under relatively extreme operating conditions. And we're excited to move into the future and to hopefully help improve the health of watersheds while also producing clean energy. So thank you very much for the opportunity to share our work, and look forward to the discussion or to questions.
Thank you so much, Abe and Sterling. It brings a lot of hope to have a positive story of how we can collect energy without minimizing our impact to the environment. So I really appreciate the work that you're doing and the time that you took to present for us today. So I'm gonna open up the floor for questions from the public. So I'm just gonna look down at my phone for a minute, see if we have any questions. So I have a couple questions coming from Phil and a comment. So he says, "This is fantastic. Eel killed at Moses Saunders Dam is so dramatic, it makes you cry. Huge congratulations. How far are you from commercialization at a scale that could replace their existing killer turbines?" So that's one part.
Yeah, so retrofit of a project such as the size that are on the main stem St. Lawrence requires sophisticated project management. And we're working on a project now. I mentioned it right at the end. We're working on a project that is opening the door to be able to show the potential for big projects like the St. Lawrence. And if everything goes well, it's entirely possible that a unit above 20 megawatts could be running before the end of this decade, and not necessarily towards the end of the decade. So in hydro terms, that's not very much time, for projects that often take decades to have anything happen. And so that's the answer is we're very actively working on on the right steps to be able to show what could be done.
Excellent, thank you. And the follow-up question he asks also, how does the power output compare currently to the units in place?
Yeah, so a lot of times the owners of hydropower facilities are compensated not only for the energy they produce, but also for the capacity to produce a certain amount of power. So literally paid for having the capacity to generate a certain number of megawatts at a particular time, as well as obviously they make money from making megawatt hours. And so we know in the design of the turbine that it's really important that the fish safe turbine has the ability to match the power output, so that the plant owner doesn't get dinged on meeting their power production capacity. And then as far as energy production, our turbines are very efficient. I mentioned that we're building 4 units now at 1.9 meters, 1.25 megawatts apiece. Those units will be between 93 and 94% efficient at their best efficiency point, and they are competitive with Kaplan style turbines down to about 60 to 70% of flow. And for projects like the St. Lawrence River, those types of projects already use fixed pitch propellers because the flow is very consistent. And so there's no need for those turbines to have adjustable pitch blades. And those are great examples of a situation where a fish-safe restoration hydro turbine could be expected to produce equivalent amount of energy and equivalent power as the existing unit. So again, the motto is fish safety without compromise.
Amazing. Thank you. Also, just it's so hopeful to hear this. I think especially for anyone who spends a lot of time on the St. Lawrence River and who see eels, it's nice to hear that there's potentially some positive changes that could happen. So kind of a follow-up question to that, somebody's asking me, how much would it cost to retrofit the Moses Saunders? And thanks for the excellent talk.
Okay, I'm not going to be able to answer that question because there's a lot that goes into it, and actually the majority of the cost has little to do with the turbine itself in those types of circumstances, because the turbines are very, very large, complex pieces of equipment. There's a lot of safety issues. So I think a lot of times it's all the other stuff that ends up driving the cost. But from the standpoint of feasibility, the turbine itself shouldn't, like the runner, shouldn't be remarkably different in its cost to produce compared to a turbine runner that's designed without regard for fish safety, just with regard for long life and efficiency and power production. Hopefully that's, yeah. I'm sorry, I can't really answer the actual question, but at the end of the day, we know the fleet is being maintained. The owners of hydropower facilities are making investments. The energy is valuable. So old turbines are being replaced, and so that's already happening. So those costs are already being accounted for, and a business case is already being found without regard for fish safety.
Great, thank you. I have another question here. So thank you for the great talk again. Are turbines safe for salmon?
Yeah, so actually our work, you might take the question.
Yeah, so we chose for the sake of time not to talk about the work that we've done with rainbow trout, which are representative salmonid species. But actually the majority of work that we've done has been with rainbow trout. So all the fundamental strike studies that we did at Alden were with rainbow trout, and then we've done a series of tests both at the small scale as well as at the larger scale in Oregon with the 1.9 meter diameter, passing trout up to 53 centimeters in length through that turbine. And what we see the same phenomenon where the fish are, the likelihood of severe strike is low because of the design of the turbine. So yes, they're another really important species that we focused on.
Thank you. So I think you had a map of all the dams and you talked about how there's a relicensing. So a question came in to ask, and maybe, I guess we'll see. They asked, do you know if the Moses Saunders Power Dam is on the list of expected relicenses?
Right. Can you answer that question?
Yeah, I should know that. I really should know that. And I don't know the exact answer to that. I apologize. that's a no-brainer. I should know that. And of course, there's a U.S. side and a Canadian side. Yeah.
Oh right, yeah. There's the American side. Yeah. I mean, I guess if ever you have the answer and people really want to know, I could send them an email or send me an email. We could put it in the chat.
Yeah.
let's see, I'm looking if we have any more questions. I know I got some text messages too, so give me just 1 second and see. So far, I think I see somebody typing to me, so maybe there's another question coming in. I don't see anything from Facebook, so give everyone just a moment. Oh, I was told that it was recently relicensed. So I got the answer.
Yeah, that's embarrassing. I should have known that.
That's okay. Okay, I think that's all I have for questions for the moment. Maybe we could leave them 1 second. Okay, everyone, last minute to send in some questions before our speakers go. So somebody asked, will there be is this presentation recorded? I believe that's what they're asking, and it will be available. It will stay on this Facebook page where you're watching it right now. You can watch it again into the future, and then otherwise we'll be also posting it to our YouTube. So you'll have 2 options to watch it. Great. Oh, I had a comment, but I think this was more of a question for the St. Lawrence or for the River Institute, but one of our, somebody who watches this quite often, he asks, so I sent him some articles today. He had a question about the eel's swim bladders and how they were impacted. So I sent him the paper that you recently published. And so I guess he was just sending me a follow-up question, but I guess I'll just say it because somebody mentioned that he posted it. So he says, it seems to me that the eels used for the research were small compared to those coming down the St. Lawrence River. Other than those entering the locks, the only way for the mature eels migrating to the sea is through the turbines. Does the River Institute have comparable data for the local dam? So part of that question for Nick, I think I'll have to get back to you by email later about that. But otherwise, I guess that is a good comment that the fish in your research were smaller than the ones that we have in the St. Lawrence River. But from my understanding, is the dam, the turbine, like the blade widths compared to the fish length, that can be changed, or would they always be the same size?
So they scale accordingly with the size of the turbine, and that is a good point. So we haven't yet had the opportunity to do testing on a large turbine with large eels, but it's something that we definitely want to do to make sure that we're seeing the same phenomenon at the larger scale.
Great.
Yeah,
Great.
yeah. And just a little bit further on that. So there are at least 3 different sites that we're in some form of planning to carry out those types of tests, which would be in the East Coast of the US. And there's a reasonable chance that one of those tests could get completed sometime, within the next 2 to 3 years. And of course, a lot has to happen for those projects to come to fruition. But that would be our best opportunity to extend the data set to include the largest, natural or wild eels that we could attain, and validate performance for those animals.
Great, thank you. And so yeah, there's some more questions that have come up since. So a really good question actually is there a strong interest from dam operators for this technology?
Yeah, I think especially as we were able to rack up hours of reliable operating time with existing references, and to share in peer-reviewed publications the fish passage data, which at least in the U.S. allows for key participants in the licensing process to then be able to make comments. I think we're seeing a lot of positive interest. Because the turbine can effectively accomplish 2 different, usually sort of unrelated goals, which are modernization and improvements in equipment reliability, and meeting license requirements of fish passage mitigation and improvement.
Great, thank you. That's good news. It's good to see that there's not like a crazy pushback or that it's being ignored.
Yeah, I think, and the reason is that we're able to design within the constraints of the existing facilities. You know, if the innovation required, you know, reconstruction, you know, and like you have to demolish a big chunk of your facility and then reconstruct it with this new idea, you'd see a lot of it just really wouldn't happen.
Right. I have another question here. So is there anything we can do as community members to encourage our local dams to look into this technology?
Yeah, I think that probably, I think the answer might be to get involved in however those facilities are regulated, because owners of hydropower facilities operate within a framework, and they're used to operating within a framework. In the US, we have a particular framework. In Canada, there's a different framework, but there's a process. So there's usually a sanctioned way of communicating, and that's probably the best way to participate. And then, like for example, there's ways to provide comments in license proceedings in the US. Otherwise, you know, we're still actively finding out who needs to know of these advances. You know, this all happened since 2019. Like in January of 2019, this was a drawing in a notebook. You know, and that's not that long ago. And the concept that an efficient modern turbine can also pass fish totally safely is just like something that's not really in the general paradigm of dealing with downstream migration. We always just think about excluding and then sending through bypasses. And it's kind of a nascent idea that process of exclusion actually itself is fraught with risks, including migratory delay, and the fact that the exclusion systems don't actually exclude all the fish. I think that, sorry, this is a long answer, but the point is, like, we're also still, I think, learning who are the right people who can help move this general idea forward. You know, and I think also we're not the only company who can think and innovate on this as well. And I think that's one of the exciting things about turbine passage, is that the most important thing is to recognize that it's possible. You know, and we're showing how to do it. And we intend to be part of that process. But the most important thing is to actually understand that this is possible. And it can really solve a lot of problems in the simplest possible way.
Thank you. I got another question. So one person said, would it be more likely that this technology would be adopted first by smaller dams to demonstrate proof the technology?
Yeah, and that's exactly what's happening. So, you know, we had to start somewhere. So the very first unit that we put in was only 21 inches in diameter, 55 centimeters in diameter. And then the next one is, you know, 1.9 meters in diameter. And then we'll install a few more of those. And now we're talking about units that are, you know, 3 meters in diameter and then 4 meters in diameter. So the power production goes from, you know, 15 kilowatts to 300 kilowatts to 1 megawatt. And now we're talking about a 20, you know, plus megawatt unit. So yeah, we have to start small, but the key is to understand that it's not limited to small systems, although it is unique. I think these design ideas that we've presented are very unique in their ability to allow for even really small turbines to be safe for fish, which is solves a big problem on the East Coast, where you have a lot of relatively smaller hydropower facilities.
I mean, considering that this was a notebook in 2019, it seems like the work has been done very quickly. So I think this is in a very near future.
Yeah, and I want to take that opportunity to give credit to our team. So the slide that I'm presenting shows a part of our team, and we have people who have been working together for many years, and a huge deal of credit goes to these people and their hard work and creativity.
Sorry, Abe, the screen wasn't sharing anymore.
Oh, sorry. Well, when I was sharing my screen, the last slide, I had a picture of a group of us. Sorry. Yeah.
It's okay. Yeah. And then, so I guess coming back to the swim bladders, could you talk more about that in eels and how their swim bladders are impacted by dams and like sudden drops in pressure?
So the issue with swim bladder injury is referred to as barotrauma, and some species are more susceptible to it than others. But basically what happens is the fish has some amount of gas in the swim bladder that it uses to regulate its position in the water column. And then when they pass through a turbine, the turbine functions based on a pressure drop. So there's a very low pressure present. And when the fish is exposed to that, the gases in the swim bladder can expand and rupture or otherwise injure the swim bladder and potentially kill the fish. Our test does not expose fish to conditions where they would necessarily see very much of that effect. So basically when fish are acclimated to a very deep setting, like a very high pressure, and then exposed to the low pressure, that's when you see really extreme barotrauma effects. So it's not something that we were specifically able to study with the tests that we did, but we are aware of deliberate barotrauma studies with eels where they're exposed to simulated pressure changes within a pressure chamber. And eels specifically haven't been found, to our knowledge, to be very susceptible to barotrauma injury. Despite that, we're trying to design turbines that are safe for fish that do have those sensitivities. And so we're working with the existing data that's out there to understand like how the turbine needs to be designed so that fish won't get hurt through barotrauma effects. And we're also embarking on some of our own original research to quantify that too.
Thank you. Nothing is left out.
We got a lot that we want to do.
I guess I think that's like the end of the question. So I'll leave it just on one comment from one of our viewers. He's just saying, thank you so much for the hopeful presentation and for caring about the fish. And I think that's a really good way to close this. So thank you again.
Thank you very much. Yeah.
All right. And good night to everybody who is watching. Thank you for tuning in. And we'll see you in February, either on Facebook Live or in person. So just stay tuned to our newsletter and our social media to learn the location of the event. So thank you, everybody, again. Thank you for all your great questions and support. And have a good night. And bye.